There are 4 objectives in this section. Develop properties of the natural exponential function. Determine the domain and range of the exponential functions. Define exponential functions that have bases other than e. Solve the exponential equations. It is likely that you have studied logarithm in an algebra course. There, without the benefit of calculus, logarithms would have been defined in terms of a base number. For example, common logarithm have a base of 10, and therefore the log of 10 to the base 10 is equal to 1. The base for the natural logarithm is defined using the fact that the natural logarithmic function is continuous, is 1 to 1, and has a range of from negative infinity to positive infinity. Once you know that the natural log of exponent is 1, you can use logarithmic properties to evaluate the natural logarithm of several other numbers. For example, we have natural log of exponent to the power n, where the power n can be moved to in front. So we have n multiply natural log of exponent, and you know that the natural log of exponent is equal to 1. So we have n, and you can evaluate natural log of exponent to the power n for various values of n. You can refer to this table and the figure. 1 over exponent 3 can be written as exponent to the power of negative 3. This is a reciprocal form. And for the x value 0.05, the x value, when you substitute into natural log function, the output is negative 3. So look at the graph. The x coordinate can be represented by exponential form. The logarithm shown in the table are convenient because the x values are integer power of exponent. You can use calculator to calculate the other function. Example, natural log of 2, natural log of 32, and so on. The function natural log of x is increasing on its entire domain. We can use vertical line test to test this function, and you will find that this is a one-to-one function, and therefore it has an inverse function. The domain of inverse function is the set of all reals, and the range is the set of all positive real. In first chapter, you have studied composite function and inverse function. Look at this part. This is a composite function involve original function and its inverse function. And you see the answer is equal to x. Correct? Original function and inverse function. So we'll get back the x. And you know that the original function is natural log function. So what is the inverse function? So that can produce x. Okay, look at this. Natural log of exponent x. So the power is x. We move the power to in front. So we have x, natural log of exponent. Then you can check your calculator. Natural log of exponent will produce 1. And we have an x. So this is a proof. The inverse function is an exponential function. Because the natural logarithmic function is 1 to 1, you can conclude that inverse function and exponent function agree for rational values of x. The inverse function of the natural logarithmic function, natural log of x, is called the natural exponential function and is denoted by inverse function of x equal to exponent to the x, and can be written as y equal to exponent x if and only if x equal to natural log of y. The inverse relationship between the natural logarithmic function and the natural exponential function can be summarized as follows. Look at this example. We have exponential equation, and look at this part. This is the exponential function, and the base is exponent, where the exponent value is 2.7. So to solve this, we need to eliminate the exponent, the base 2.7. So we apply the log base 2.7 or the log base exponent. Do you still remember the log base exponent is natural log? So look at this. We apply natural log, okay, at both sides, and then for right side, since the natural log and exponent they are an inverse function, so we just eliminate the exponential function, and the right side just only left x plus 1. And in order to get the x, so we move plus 1 to left side, so would be minus 1. So you can check with your calculator the value of x equal to 0.946, and you can check this solution. You substitute in the negative 1 plus natural log of 7 into the original equation, and you will get back the answer is 7. Here are the exponential function operations. Let a and b be any real numbers. We have a find operation here. You must alert for the first and the second operation. I show you the common mistake. Look at the first one, exponent to the a multiply the exponent to the b will equal to exponent to the a plus b. So look at the common mistake made by a student. Exponent to the a plus exponent to the b is not equal to the exponent a multiply b. And for the second, exponent to the a minus exponent to the b is not equal to exponent a divided by b. And for the third one, exponent 0 is equal to 1, and the fourth is a reciprocal, and the fifth is a power of root. An inverse function share many properties with original function. So, the natural exponential function inherits the following properties from the natural logarithmic function. For the first one, the domain of exponential function is from negative infinity to positive infinity, where the range is from 0 to positive infinity. Do you still remember the domain of natural log function is from 0 to positive infinity, and the range of natural log function is from negative infinity to positive infinity, right? Look at the second. The function f(x) equal to exponent to the x is continuous, increasing, and one-to-one on its entire domain. So the second property is totally same as the natural log function. The graph of exponent x is concave outward, but the graph of natural log function is concave downward. Fourth property. You see, this is an exponential curve, exponent to the x. And when the x tends to negative infinity, so meaning that in this slide, negative infinity, and here is positive infinity. And look at the curve. When the curve continues towards left, the limit exponent to the x, when x tends to negative infinity, will equal to 0, meaning that the curve will closer to 0, y equal to 0. And for the fifth, limit exponent to the x, when x tends to positive infinity, is equal to infinity, meaning that when the x tends to this direction, to the positive infinity, the curve is increasing without bound, because infinity. This is a summary for the properties of the natural exponential function. You can go through once again, where this is similar to the previous page. A function f defined by f(x) equal to exponent x is an exponential function, since the expression exponent x represents a real number for all real number of x. Therefore, the domain of an exponential function is a set of all real numbers. Note that exponent x is a function f is always positive for all real value of x. So look at this. All real value of x, so meaning that the x value, no matter is negative and positive, but the function is always x positive side. So the range of function is a set of all positive real number. Notice that as x tends to negative infinity, this is a negative infinity direction. For the x-axis, negative infinity. the curve closer to 0. You see, this is a x-axis. The curve will closer to 0, but not touch on y equal to 0. And the line y equal to 0 is an asymptote. As x increases, exponent x increases, so the curve increases. So the range of this function is y greater than 0. Same for the exponential function, as the power is rational function. For example, exponent to the power of negative x. When x tends to positive infinity in this direction, the curve will closer to 0, meaning that x increases, the curve decreases. And for the properties of this function, same as the exponent to the power x, you see the curve still concave upward, and the domain and range. The domain of this function is all real numbers, and for the range is greater than 0. Sketch the graph for each of the following exponential function and determine its range. For the first function, 1 plus exponent x, when x tends to negative infinity, the function tends to 0. Then fx tends to 1. Y equal to 1 is an asymptote line. I show you the working. For the function fx, tend to 1 plus exponent x, and when x tend to negative infinity, so you can construct one table to test. You see here is exponent, here is x. And here is exponent x. Okay, so because we study the x tend to negative infinity, so in this direction. So try negative 1, negative 5, negative 10, let's say negative 100, and so on to infinity. So we have a value for the x equal to negative 1. The value is about 0.3679. And for the x equal to negative 5, the value getting smaller. And to the negative 10, getting smaller. 4.54 times 10 to the power of negative 5. And you can check for the negative 100 and so on. The value, you observe the value here. The value here is getting smaller. So you can conclude when the exponent to the power negative infinity, here negative infinity, so the value almost equal to 0, very small, closer to 0, so we have 1, so that the curve tend to 1. The curve, when x towards this direction, the curve will closer to 1. So y equal to 1 is an asymptote line. When x equal to 0, we check for the y asymptote. We check for the y intercept. So we let x equal to 0. So f0 equal to 2, meaning that you just need to substitute your x by 0. So exponent 0 is 1. So 1 plus 1, 2. So the y-intercept here, 2. When x increases, fx increases. Is it true? You can prove. I show you once. So fx tends to 1 plus exponent x. We have studied when the the curve towards left, the curve will closer to 1. And now we try to study when the curve tends to right side. When x tend to positive infinity. This side is positive infinity. Of x tend to positive infinity of x value. So fx tend to 1 plus exponent infinity. So just contract table to test it. The value here is x and exponent x. For this side, the value, okay, you can test some of the value, 5, 10, 100, and until infinity. And for the x equal to 1, all of you know the value is 2.7. And for the x equal to 5, the value getting bigger, 148.4132. And how about x equal to 10? The value is 22,026.4658. So you can see the value is getting bigger. So meaning that when x getting bigger, the value, so the output getting bigger, meaning that the curve will increase without bound, without limit. So will tend to infinity without limit. So this is a curve. Okay, so to study the range, look at the curve. The curve it starts from y equal to 1, but exclude the 1, because y equal to 1 is an asymptote line. So the range is greater than 1. For second function, we have 2 exponent to the negative x minus 3. When x tends to positive infinity, you can use the method I show you in A part to study the both sides. Look at this one, when x tends to positive infinity, so meaning that study this direction, x tends to this direction, positive infinity. So the value for this function will be closer to 0. So we have gx tend to -3. And we study the y-intercept. So we substitute x equal to 0. For y-intercept, you just substitute. Okay, I show you the working. G0 to exponent -0 to check the y-intercept -3, where the exponent 0 is equal to 1. So we have 2 minus 3 is equal to -1. So here, y-intercept. And you can check for the x-intercept. You just let y equal to 0. Let y equal to 0. So you solve exponential function. You have learned how to solve exponential function. Refer back to the first example in this slide. We have 2 exponent to the negative x minus 3 equal to 0. So we move the -3 to right side. So we will have 2 exponent negative x equal to 3 and 2. Move to right side, we will have 3 over 2. And because this is an exponential function, the base is exponent. So we need to apply the log base exponent, which is natural log. So we have natural log of exponent to the negative x equal to natural log of 3 over 2. So can be written as negative x equal to natural log of 3 over 2. And you solve the x. So now we have negative natural log of 3 over 2. Here is negative natural log of 3 over 2. Okay, the x-intercept. So after you have these 2 points, so you can sketch the curve. Because you know the power here is negative. So the curve is decreasing from left to right. And from your curve, you know that the range is from -3 to positive infinity. The base of the natural exponential function is exponent. This natural base can be used to assign a meaning to a general base a. If a is a positive real number but not equal to 1, and x is any real number, then the exponential function to the base a is denoted by a power to the x and can be defined by exponent to the power of x into natural log of a. If a equal to 1, then y is equal to 1 power to the x, and which is 1, and is a constant function. Here they are exponential function that have bases other than e. A is any constant. Their properties same as the properties of natural exponential function. Without using a calculator, calculate 8 to the power of 2/3. This is one of the example. The exponential function that has the base other than e. The base here is 8. is not exponent. We can use the fourth property, where the 2/3 can be written as 2 multiply 1/3, and 8 power to the 1/3 is cube root of 8, which is 2. And after that, we have square. So 2 power to the square is 4. This is an exponential equation that has base other than e. The base here is 2, and here also 2. So to solve this exponential equation, you need to form it to quadratic equation. First, we write back the original equation. And for the first term, you can use the fourth property, where the 2x is equal to x multiplied by 2. So, can be written as 2 power to the x and power 2 minus 5 times 2 power to the x plus 4 equal to 0. And you let y equal to the 2 power to the x. So, your exponential equation can be written in quadratic equation. Y squared minus 5y plus 4 equal to 0. And you solve this quadratic equation. You factorize. And then, let the first factor equal to 0. So we have y equal to 4. And replace back the y equal to the x. We have x to power to the x equal to 4. And you can change 2 power to the 2. Then by comparing method, x is equal to 2. And second factor, let equal to 0. We have y equal to 1. And again, change back the y to 2 power to the x equal to 1. And you can change the 1 to 2 power to the 0. So the x is equal to 0. And you can conclude x are 0 and 2. This is the application part when modeling the half-life of a radioactive sample. It is convenient to use half as the base of the exponential model. Half-life is the number of years required for half of the atom in a sample of radioactive material to decay. The half-life of carbon-14 is about 5,715 years. A sample contains 1 gram of carbon-14. How much will be present in 10,000 years? Based on the question here, the model is not given. So, we should form a model. Before we form a model, we should introduce the variable that we need to use to form a model. We introduce t as time and y as amount of carbon-14 measured in grams. And we let t equal to 0 represent the present time. Using a base of half, you can model y by the equation y equal to half power to the t over 5715. And you need to verify the model that you have created. First, you can substitute t equal to 5715 into your model, and you calculate The answer here is half gram. Is it true? Look at the question. A sample contains 1 gram of carbon, meaning that this is the initial time. So a sample originally is 1 gram. Then after 5,715 years, the sample weight reduced to half gram. So just left half gram. So correct. And second, you can verify by initial time. So initially, your sample is 1 gram. So you can substitute your T by 0. So 0 divided by anything is equal to 0. So half power to the 0. So half power to the 0 is 1. So meaning that you see, when you substitute T equal to 0, initially your sample is 1 gram. So you can conclude your model is correct. You can keep verifying your model by you substitute the T equal to 11,430 years. Then the amount is reduced to a quarter of the original amount. To find the amount of carbon-14 after 10,000 years, you substitute the 10,000 into T. And you calculate. The sample is 0.3 gram. And you can plot the graph out. Now that your curve is decreasing, because your model is decay model, the base is half.